Hello, this is VLMD Rounds, a podcast on medical science and tools to optimize your health. I'm Dr. Vivian Lowe. In my last episode, I talked about LDL and atherosclerosis, and basically, I was using that to be the start of a series that I'm doing on atherosclerosis. And what I want to do in the next few episodes is just to lay out all the different aspects of atherosclerosis that contribute to the disease process. Now, I made the proposal in that last episode that in the end, I think that atherosclerosis is an autoimmune disease. So it's up to me now in the next few weeks to justify that assertion, to, show you the different aspects of this autoimmunity. And that's what we'll be doing. In that episode, I also mentioned that it really is the LDL itself that is the neoantigen, and that cholesterol content is not prime in initiating the process. I did say, however, that it does have a role. So it doesn't mean that cholesterol has nothing to do with the atherosclerosis process. It's just that it's going to have a role that we don't actually usually think about. So that's why this episode we're going to focus on cholesterol and its role in atherosclerosis. Let's go. All right, I have my notes because I want to try and keep this under 30 minutes or so. The three things that we're going to tackle today. First off, I'm going to give a brief review on cholesterol metabolism and talk about the pools of cholesterol in a cell. And then I'm going to go into cholesterol's role in inflammation and, talk about different cells in the immune system. Primarily, I'm going to focus more on the macrophages, so on the innate side of the immune system, but I'll also just, point out other cells that might be involved, just so you have an idea of how cholesterol affects the entirety of the immune system. And then finally, I am going to talk about chronic inflammation using the model of rheumatoid arthritis. It's an autoimmune disease, and people with rheumatoid arthritis have chronic inflammation. So what do we see happening there with cholesterol in that model of chronic inflammation? All right, now let's start with the cholesterol metabolism. And as you know, cholesterol can be synthesized by your cell. It's a long multi-step process that we call the mevalonate pathway, and there are over 20 plus enzymes involved. So it's very complicated. We're not going to go into detail. Now, all these enzymes that are involved and that whole process is happening in the endoplasmic reticulum. And you can think of the endoplasmic reticulum as these tunnels that extend out from the nuclear membrane. So you have the nucleus, and the nucleus of the cell obviously has a nuclear membrane. And then, the nuclear membrane actually kind of leads into this tunnel system of membranes that we can call the endoplasmic reticulum. All right, now, there is a transcription factor that lives there. So the transcription factor is called SREBP2. And let's just pretend it's a dragon that lives in the tunnels of the endoplasmic reticulum. All right, so we have this dragon, SREBP2. And most times it's pretty content to just hang out in the endoplasmic reticulum. It's quite happy dozing away in the tunnel system, except when it senses that cholesterol levels in the cell are dropping. Now, when this happens, our dragon springs into action, right? And the first thing it has to do, it has to go to the Golgi body, and this is associated with the endoplasmic reticulum. And it goes to the Golgi because the Golgi, usually you can think of it as the shipping department. It helps prepare for shipping substances out to different parts of the cell. So our dragon goes to the Golgi body, and there it gets modified in such a way that now it can travel travel where? Well, it's going to travel to the nucleus because, as I said, it's a transcription factor. So SREBP now goes to the nucleus, and there it's going to activate genes that will make the enzymes that are involved in forming cholesterol. So as a result of that, what are we doing? We're upregulating the synthesis, the making of cholesterol. So SREBP2 can help us raise cholesterol levels in the cell when those levels start to fall. Now, besides making your own cholesterol in the cell, the other thing you can do is, why don't we import some cholesterol? And we do that through the LDL receptor. All right, so we're taking in the LDL, which is loaded with cholesterol, and then now we can access the cholesterol that way. So that's pretty smart too. So SREBP2 also regulates the transcription of genes to make more LDL receptor, and that way we can import more LDL, hence more cholesterol, into the cell. And then when the levels of cholesterol now are where they need to be, then our little dragon, the SREBP2, will go back to its tunnels in the endoplasmic reticulum and just go back to sleep there. All right, so its main job is to raise cholesterol levels either by increasing synthesis or by bringing it in through the LDL receptor. Now, there is no breakdown or catabolic pathway for cholesterol in the cell, and we don't want a lot of free cholesterol sitting around because free cholesterol can be very toxic. And so what we can do is, well, we can take this cholesterol and we can make it in the form of cholesterol esters, and that means we combine it with fatty acids. And this makes it a lot safer and more stable, right? So we can esterify it, which means we combine it with fatty acids. And once we have done that, we can now store these cholesterol esters in lipid droplets in the cell. So it's kind of like a pool of the cholesterol and other lipids there. So we have these lipid droplets that sit in the cell. Or we can use the cholesterol for organelles, right? Because these organelles have membranes as well, and also for the plasma membrane. And then finally, what else can we do with the cholesterol? We can get rid of it. Why don't we ship it out of the cell? Now, for this export function, we have to depend on LXR. LXR stands for liver X receptors, and these are nuclear receptors, and they live out in the cytoplasm. And basically what happens is that they sense when cholesterol levels are too high. And as the cholesterol levels rise, then LXR is going to move to the nucleus, and there it's going to turn on genes for making these cholesterol transporters. And you'll remember some of the names, ABCA1, ABCG1. These I talked about in the lipoprotein episode, right? And, it's not important to remember the name, but you just remember that these are transporters that are going to take the cholesterol out of the cell. So that's what happens when you have high levels of cholesterol. We activate LXR to go to the nucleus. There they turn on genes to make more ABCA1, ABCG1, and these are going to carry the cholesterol out of the cell. So you see there's a nice regulation pattern here. We have the SREBP2 dragon living in the endoplasmic reticulum that will actually increase cholesterol synthesis and bring in more cholesterol when cholesterol levels are low in the cell. And then conversely, we also have the LXRs, and these are going to actually go to the nucleus when cholesterol levels are too high. And this is going to activate genes that will make more of this cholesterol transporters and take the cholesterol out of the cell. Now, let's briefly talk about the different pools of cholesterol in the plasma membrane, because when we say cholesterol, it's not like all cholesterol can be used by the cell, all right? So 30% of the plasma membrane is made up of cholesterol, and we have what we call the accessible or metabolically active pool of cholesterol. This is a small fraction of the plasma membrane cholesterol content, right? And it's very variable in terms of how much of this accessible pool you have there. But we know it's basically in equilibrium with the endoplasmic reticulum. And this means that really it can be sensed by our dragon, the SREBP2, in the endoplasmic reticulum because it's in equilibrium with the cholesterol in the endoplasmic reticulum. And so now it's under control of SREBP2. So that's the accessible or metabolically active pool of cholesterol. We have another pool called the sphingomyelin associated pool. Now, sphingomyelin is a lipid, and we find a lot of the sphingomyelin in domains of the plasma membrane that we call lipid rafts, RAFTS. And these lipid rafts are, you can think of them as platforms that are studded with these sphingomyelin compounds as well as cholesterol. And the reason for it is that when we have these rafts, right, we have to have a very solid and stable structure because a lot of receptors for the cell sit in those lipid rafts. And these receptors can be very large, right? These proteins, sometimes they cross the membrane layer several times. So they're bulky and they're big, and they need to have a good platform to sit on. And that's why we have these lipid rafts that are made of sphingomyelin and also of cholesterol. So this pool of cholesterol is very stable. It really doesn't change very much with acute levels of cholesterol accumulation or depletion in the cell. And it doesn't equilibrate generally with the endoplasmic reticulum pool. So it's separate from that. But we can see that in certain circumstances, when we have invasion by some microorganisms, for example, we can have some bacterial enzymes that can dissolve those lipid rafts. And as a result, we free the cholesterol there. And that cholesterol now can go into other plasma membrane pools, all right? So maybe some of that even goes into the accessible pool. So you can see we can impact the cholesterol pools this way when we have an infection by microorganisms. And finally, we have what we call the essential pool. And this basically is the remainder of the cholesterol. It plays a role in the overall integrity of the plasma membrane. And, you know, the cholesterol that's in the essential pool, it's quite resistant, and you really have to subject it to pretty strong chemicals to kind of deplete the plasma membrane of that cholesterol. But when you manage to do that, the cell is going to shut down and die. Because after all, cholesterol is vital to life. I don't think we emphasize that enough, right? So if you get rid of the cholesterol, your cells die. And when your cells die, well, basically, see you in the next dimension, okay? Because you won't be around either, right? So we need that essential pool of cholesterol. All right, so now we talked about the different pools, and basically the ones that we really care about would be the metabolically active pool or the accessible pool, and maybe sometimes in certain cases when we're under attack by microorganisms, that sphingomyelin pool might get involved as well. Let's look at the role now of cholesterol in inflammation. And it turns out that cholesterol metabolism controls the function and activity of your immune cells. All right, so cholesterol metabolism, lipid metabolism in general, is very important to immune cells, okay? Because if you think about it, when immune cells encounter an antigen, some kind of microorganism, some danger signal, there's no time to waste. They have to spring into action really quickly. They have to divide, proliferate, and then just go on the attack and start signaling to rev up the immune system, to rev up the immune response. So there's a strong link between the immune response and metabolism. Why? Because when that happens, your immune cells are going to need resources. They're going to need energy, more ATP, please. they're going to need substrates, they're going to need metabolites because they're making all these proteins to signal, all these cytokines, for example. So we need those resources to drive the immune response. All right, and so cholesterol metabolism is a great resource to these immune cells to help drive the immune response. Now, on the other hand, those microorganisms also are eyeing that cholesterol. Why? Because they are also needing to grow and proliferate, right? So, as usual, it's a battle for resources. Microorganisms that are invading, they need the lipids and the cholesterol to build membranes, right? And to travel around in your body. And so they too will need the cholesterol, and they often try to steal that from your cells. And it would be great if they could just kind of get the cholesterol from our cells, because they wouldn't have to devote any resources to making their own. So in the case of innate immune cells, for example, like macrophages, what they can do is they can sense danger through these special pattern-associated, these pathogen-related receptors that we call toll-like receptors. I talked about it in the previous episode, right? These toll-like receptors can sense danger, they can sense invasion by microorganisms, because all these microorganisms have conserved structures that are pretty generic and recognizable by these toll-like receptors. And when this happens, a lot of times the activation of the signaling of toll-like receptors will also engage interferon 1 receptors. And what happens now? With interferon signaling, we're going to decrease the cholesterol metabolism in the cell overall, right? Generally, when we see interferon 1 activated, we're going to actually decrease cholesterol metabolism. Why? Well, the thinking is we won't then provide all this cholesterol to the invading organism. We're just going to deprive them of this very valuable resource, right? So that's one way, for example, that we can use cholesterol mechanism in our defense system. Also, when you have excess endoplasmic reticulum cholesterol, well, we can activate an immune complex in your cell called the inflammasome. And essentially, this is a big protein structure, right? And all these different protein units come together and make this mega structure that we call the inflammasome. And the inflammasome essentially helps to create active cytokines, inflammatory cytokines, all right? So we have these cytokines that are in their dormant form, and once we activate the inflammasome, then we're going to convert the dormant cytokines into their active form, and now we have active inflammatory signaling through those cytokines, all right? So those are inflammasomes, and when you have excess cholesterol in the ER, we can activate those inflammasomes. In addition, we start to damage the mitochondria, and this will result in some mitochondrial DNA getting out into the cytosol of the cell, which is not a great thing, and that will activate another inflammasome and again lead to more pro-inflammatory signaling. Now, if we go back to the toll-like receptor 4, right, that regulates SREBP2 and also LXR. And it's a pretty complex kind of pathway, but I just want to tell you that when you have toll-like receptor 4 signaling happening, right, the macrophages are picking up some of these danger signals through that receptor, then the net effect is to inhibit SREBP2 processing, right? So we're going to inhibit that dragon from moving to the nucleus. We're going to keep it in the endoplasmic reticulum. In addition, we're going to induce formation of oxysterols like 25-hydroxycholesterol. I talked about that in the episode on oxysterol, so you can look that up. But basically now when we have 25 hydroxy cholesterol floating around, that's going to activate LXR. And you know what happens when LXR is activated? We're going to increase those cholesterol transporters, ABCA1, for example, and then we're going to shuttle the cholesterol out of the cell. And we're actually depleting the levels of cholesterol within the cell. We're not making any, we're not bringing in any, and we're exporting the cholesterol that we have. So decreasing the cholesterol content there, and this now feeds back to the TLR signaling, those receptors, and decreases that signaling. So it kind of decreases the inflammation and dampens the inflammatory effect that way by decreasing the cholesterol levels in the cell. And it turns out that when we look at animal models, mice that are deficient in LXR, for example, they are more susceptible to intracellular infection, because if they don't have LXR, they can't export the cholesterol. We have more cholesterol in the cell, and these intracellular organisms can use that cholesterol to their benefit, right? So they're more susceptible to these intracellular infections. Also, when you give mice the LXR agonist, right, then what we see is we increase the LXR effect, which basically means that we increase the export of cholesterol. And this decreases inflammation in lupus models of autoimmunity, right? So we're actually downregulating the immune system that way. Now, the immune signals themselves can regulate cholesterol metabolism. And so, for example, when we have that toll-like receptor signaling, we pick up these dangerous signals through that toll-like receptor. We make tumor necrosis factor alpha as a result, TNF alpha. Well, it turns out macrophages that are exposed to TNF alpha, they're actually going to send signals for wound healing and resolution of infection. So it kind of calms down the immune system. But high levels of TNF alpha and long exposure actually leads to pro-inflammatory signals, right? So it's going to be time dependent. So TNF alpha in the short term upregulates that ABCA1 expression, so we're going to get rid of cholesterol there, and that's in the early phase, right? About 3 hours. But at 24 hours, if we have continued TNF alpha there, now we're going to start to activate the dragon, right? SREBP2, and we're going to increase cholesterol synthesis and therefore increase the pro-inflammatory response. So you can see this is also time dependent. The immune system isn't simplistic. I've said this many times, and the context really matters. The tissue matters, the type of cell matters, and the time interval also matters. Now, I talked about the macrophages. I'm just going to talk about another innate cell, just to give you a glimpse of how cholesterol affects other cells, other immune cells. So let's talk about neutrophils. Neutrophils are very good at killing, and they're well known for forming something called nets, and that stands for neutrophil extracellular traps. And basically what happens is that they're able to self-destruct, right? To protect your body, what they do is they're going to self-destruct by spitting out their DNA in a kind of web, all right? Almost like a little spider web, right? And they shoot it out, and this traps microorganisms, and it's very toxic to the microorganisms. So they're well known for these nets that they make. Now, when we treat with statins, we notice that we decrease the cholesterol content in the membranes, and actually this promotes more net formation. So we're going to have more of this destruction of the neutrophils as they spit out this toxic DNA. And there's increased reactive oxygen species and increase in interleukin-1 beta, which is a very inflammatory cytokine. So actually, when we deplete the cholesterol content of the cell through the use of statins, we are upregulating the immune response in the neutrophils there, right? So as you can see, different cells, different contexts, and we'll get a different response. What about the adaptive cells? So very complex here. I'm just going to give you a glimpse of some of the effects of cholesterol here. So with T cells, the landmark study was done by Bensinger et al. And basically Bensinger's group showed a link between T cell receptor signaling and suppression of LXR. So remember, LXR does what? It gets cholesterol out of the cell, right? But if you suppress LXR, what's going to happen? Then you're going to accumulate cholesterol in the cell, opposite effect, right? Well, when you have T cell receptor signaling, the T cell picks up an antigen that matches its T cell receptor, then it's going to start to proliferate, right? We're going to make more of these T cells that recognize that antigen. But when we do that, we're going to suppress the LXR signaling. And the reason for this is we are trying to accumulate cholesterol in the cell so we can have T cell proliferation. I told you it's really important for cells to have cholesterol to grow, to proliferate, and to differentiate. So we're going to need that cholesterol. So don't export it, leave it in the cell. With B cells, for example, the membrane fluidity is really important, right? And it depends a lot on the cholesterol content. So it alters the B cell antigen presentation and also B cell receptor signaling. And turns out that the membrane cholesterol content in the B cells varies a lot at different stages of B cell activation. Okay, so it's again very, very dynamic here, and you have to look at the context and the different stages of activation. Okay, finally, let's look at a chronic inflammatory model here. And I told you I'd be looking at rheumatoid arthritis. It is an autoimmune disease. And, this autoimmune disease is associated with a chronic inflammatory process here. And because of this chronic inflammation, rheumatoid arthritis patients are at higher cardiometabolic risk, right? It turns out they are at a 1.5-fold higher risk for cardiovascular disease than the general population. So the assumption has always been that these people, they have a lot of cardiovascular disease, so their cholesterol must be off the charts here, must be very high. But when they were doing clinical trials to study the use of biologics, right, in treating these autoimmune patients, it turns out when they measured the serum cholesterol, they actually had low levels when the patients were in a highly inflammatory phase. And conversely, when we treated the patient now with biologics, so these are, drugs like tumor necrosis factor alpha inhibitors or interleukin-6 inhibitors, right? So we're trying to downregulate the inflammation in those patients by giving these cytokine inhibitors. Well, when we do that, number one, the patient's symptoms resolve, they get better, right? And it turns out that actually the cholesterol levels start to rise in the serum as they get better. When they respond to those meds, we see a rise. And people who respond to TNF alpha inhibitors and interleukin-6 inhibitors, they not only have a rise in the cholesterol, they actually have less cardiovascular disease. Very interesting, don't you think? So this means that in this chronic inflammatory model, increased cholesterol doesn't mean an increased risk in cardiovascular disease. Actually, it was the lower cholesterol content that put them at higher risk. And the increased serum cholesterol as they were improving might impact the flux of cholesterol in the cell that leads to immune mechanisms of tolerance. All right, finally, I just want to mention this one other study, small one. They had like 18 healthy individuals there, healthy people, and they just gave them statins for 28 days. And what they noted was that there was an increase in pro-inflammatory cytokines in the serum as the LDL content dropped. I mean, they halved the LDL content. It went down to about 45 milligrams per deciliter in most of those patients. And actually they saw a rise, concurrent rise in pro-inflammatory cytokines that actually stayed about 2 weeks after they stopped giving the statins. We still saw this increase in pro-inflammatory signaling. Now, granted, it was a pretty modest increase, but it seemed suggestive that when we played around with the cholesterol levels, that we actually were revving up the immune system there. So you can see there is duality in cholesterol metabolism, in the sense that it can set you up for pro-inflammatory conditions and also anti-inflammatory conditions. There are so many immune and cellular processes that are linked to cholesterol synthesis. It's really very hard to study. And yes, there's a lot of attention to it now. I just gave you a very broad overview because, to have gone into depth, I would have needed several hours. Okay, so again, I just gave you a sprinkling. Some of the reactions are very complex because, again, with different aspects of the cholesterol metabolism, different parts of the pathway, we could upregulate certain types of T cells, the more inflammatory kinds, or we could actually promote more of the Tregs, for example, depending on how that pathway went. Okay, so highly complex. And the main thing I want to emphasize is cholesterol does have a role, right? Because it impacts the immune function and the activity of those immune cells. So if we're talking about atherosclerosis as an autoimmune disease, you're going to bet that cholesterol is involved because it's modifying the inflammatory response depending on what we see. But, with that chronic inflammatory model of rheumatoid arthritis, very interesting that with the increase in cholesterol, we actually saw that patients were getting better. And similarly, we see that in plaques, right? When we look at the macrophages that are chock full of cholesterol, the foam cells, right? Those actually tend to have an anti-inflammatory profile, and it is the cholesterol depleted, the macrophages that don't have cholesterol in them, that don't have the lipids in them, the non-foam cell macrophages, that actually have a more inflammatory profile, right? A lot of those cells, right, we just say, oh, it's macrophages, it's foam cells, and we assume the foam cells are more inflammatory, and yet they have more of the M2 sort of more anti-inflammatory profile as compared to other macrophages that are found in the plaque. And also, a lot of the LDL, for example, that's found in plaque are also quite deficient in cholesterol as well. So you can see it's very complex here, but yes, cholesterol does have quite an important role. It's not quite the one that we imagined, right? But it plays a role in how those immune cells function. So I hope that you will join me in my next Q&A session. I hope to have done a few of these episodes now, laying out different aspects of this autoimmune process that we call atherosclerosis, right? And I'd love to have some conversations with you at my Q&A, get some of your questions, some of your comments, some of your thoughts on this. And you can check out my schedule for those events on my website, vivianlohmd.com. VYVYANELOHMD.com, and I'll put that link in the description. And also, some of you have reached out and asked how you could work with me. So thank you very much for getting in touch with me. Now, I do have an online platform that I've developed. It's my Metabolic Foundations platform, and this is now available to people everywhere. So you don't have to be in the Boston area where I'm situated right now. So wherever you are, you could work with me through this platform. And it's basically a program to help you reset your metabolic health. And it involves a lot of components, different components like videos and PDFs and different resources, but also live sessions with me to get your questions answered. Also coaching, right? And just so I can extend my teaching that way as well. So if you're interested in working with me that way, go to tulaversity.com, TULAVERSITY.com. So it's essentially Tula, Tula, and then versity as in university. Tulaversity.com. I'll put the link in the description as well. And I am thrilled that I think I'm going to get this under 35 minutes. That's been my goal, to just try and limit these episodes, make them short, but fill them with the essential details. And in the next episode, I'm going to continue on in my series on atherosclerosis. So look out for it. But for now, signing out from VLMD Rounds, I'm Dr. Vivian Lowe, and I sing the body electric. Bye.